Hi, my name is Keshav. I am from CSC Data Science, and today our subject is Applied Physics. In Applied Physics, our topic was formulating and solving routing problems on quantum computers. Now we are going to start from introduction. Routing problems encompass a wide range of problems in logistics and operations research. These problems are generally concerned with the optimal management of fleet of vehicles. Example, how should each vehicle be dispatched in order to satisfy some goal while minimizing time or maximizing profit? There are many variants and specifications of the problem to certain settings, and this focus work on vehicle routing problem with time windows VRPTW. Typical solution approaches the VRPTW on classical computing devices include mathematical formulations involving discrete variables. Consequently, classical methods tend to have worst case solution times that exponentially with the number of decision variables. The 0 to 1 integer programming feasibility problem is NP complete. For specific applications, tailored exact approaches, mathematics need to be devised such as aim of obtaining solutions with good quality at reasonable computational effort. For example, we are motivated by the maritime inventory routing problem MIRP, in which the inventory levels of the product must be tracked. This is a characteristic of commodity and bulk. Example, oil, gas, iron ore, grain, shipping with which in 2017 accounted for 75% of world seaborne trade measured in ton miles. Recent work in 6 indicates the limits of some of these classical movements MIRP. The ongoing evaluation of quantum computing hardware and the recent advances of quantum algorithms for mathematical programming make decision making for routing problems an avenue of research worthwhile to be explored on quantum devices. So far, quantum algorithms for mathematical optimization have often focused on quadratic unconstrained binary optimization QUBO, expressed in the form min of x power t mx plus c. St of x belongs to 0, 1 whole power n. This is the formula for quantum algorithms for mathematical optimization, where M is an n into n real matrix and C is scalar offset. To achieve the representation on quantum devices, the QUBO can be transformed into an Ising model of Hamilton constituted as a summation of weighted tensor products of Z-Pauli operators. Equality constraint can be also be added to the QUBO formulation by casting them as quadratic penalization of the code objective function. One of the goals of our work is then to introduce formulations of the routing problem that are amenable to emerging quantum hardware and quad algorithms, which can provide the fast heuristics for QUBO problems. And this was a figure of small example VRPTW R cos Cij equal to the time travel time. This is near a fully graph. However, travel from node 3 to node 2 is not allowed because the time window of the node 2 can time window of the node 3 begins. The vehicles leave depot day fully loaded at their capacity Q is equal to 6. QA is a negative or demand must be delivered as a depletes the product on variable. The article aims to bring together different formulations for solving routing problems on quantum devices with specific focus on timing constraints expressed either in discrete or continuous form. These formulations are largely inspired by the classical operation research literature. We introduce them here in order to obtain QBO representations suitable for quantum algorithms. Previous work on quantum or quantum inspired classical algorithms applied to logistics problems has focused on traveling salesman problem or related to the capacited vehicle routing problem. Overall, the contributions of this article are the following. We introduce the mathematical optimization models for VRPTW suitable for state-art quantum algorithms. We investigate the modeling capabilities of VRPTW formulations with respect to constraints and objectives arising in practical applications. We compare the VRPTW formulations from quantum computing perspective, specifically with matrices metrics to evaluate the difficulty in solving the underlying QBO problems. We test the formulations on stimulated gate-based quantum devices and draw insights on the current capabilities of the quantum computing approaches the routing problems. Given that the quantum algorithms proposed here for the VRPTW are not bound to a specific quantum QBO solver, our framework is flexible for the future improvements in both gate-based quantum hardware and algorithms, as well as other type of emerging specialized devices. This is especially appealing given the wealth of studies and results in this direction. The rest of this article is organized as follows. Section 2 describes VRPTW problem that we consider along with the key features of MIRP that can be cast in the VRPTW formalism. The various mathematical programming formulations are VRPTW are introduced in sections 2B, 2E. In section 3, we discuss how to cast the solve the VRPTW formulations on quantum devices via reformulations of QUBO problems. See section 3A and 3B or an MBO problem, section 3C. Section 4 compares the formulations along the different dimensions on the examples presented in section 4A. In particular, the strengths and weaknesses of formulations in modeling VRPTW are discussed in section 4B, while the difficulty for solving the formulations is evaluated in sections 4C and 4D, where the number of variables, sparsity of the QBO matrix, and the number of solutions. Section 4E includes numerical results obtained from solving a VRPTW instance with the outlined quantum algorithms, sequence-based formulations and sequence-based formulation with continuous solved in section. Finally, conclusions and remarks are drawn in section 5. Now we are going to discuss about solving the routing problems on quantum computers. In this section, we discuss the reformulations needed to express the VRPTW formulations in from suitable for the quantum algorithms. In sections 3A and 3B, most of the formulations are cast into one, which is a standard form of QBO and enables the application of quantum algorithms such as VQE and QAOA. Due to the presence of continuous arrival times, the sequence-based formulations with continuous time as presented in section 2E is an MBO and different representation on quantum devices which are discussed in the later sections. A root and arc-based formulations as QO. Problems 2 and 3 have common form. For real value vectors B and C and the real matrix A. This challenge is to be construct matrix M so that the cubo standard form in 1 is equivalent to the binary linear program. Specifically, we would like our matrix to encode the quadratic penalty function. For real constant pi is greater than 0 to be determined, this transformation is an exact penalty reformulation of 7 and consistent with the general suggestion of binary linear programs from as well as the form transformation specific to set the partitioning problem from 21 section 4.1. The main challenge is the finding the right value of the p so that the mineralization of h is equivalent to 7. The general reasoning is as follows. Sequence-based formulation as QBO. The sequence-based formulation differs from the root-n and arc-based formulations since it has bilinear quality constraints. To devise the QBO for reformulation, express the linear quality constraints and foresee as Ax equal to B. Similarly, along with the bilinear equality constraints and foresee these are turned into penalty term. For penalty parameter pi, sufficiently large solutions, therefore, and 8 coincide. Looking the specifies constraints and considering the variables are binary and smallest value that are penalty term Pw of x can take for an infeasible solution as P. We are PTW via admin based heuristic. In order to extend the range of mathematical formalization solvable on quantum near-term devices via variational-based approaches, Gambel and Simonetto proposed a multi-block ADMM operator splitting procedure. This iterative algorithm devises a decomposition for a specific class of MBOs into a QBO subproblem to be solved by the QBO solver oracle on near-term quantum devices by quantum algorithms such as VQE on QAOA. Consider the cubic non-convex constraints of the sequence-based formulations with the continuous times, namely, the idea is to deal with them is a continuous problem of ADMM framework by using sequential convex programming. In particular, since we are splitting the problem into the binary variables, we introduce continuous variable for each 3 indexed binary variable. Then in the continuous problem of the ADMM, the where constraints phi l minus phi m will become. Comparison of formulations. First, in section 4a, we describe two examples that will be several benchmarks compared to the mathematical formulations from a quantum computing perspective. Demonstrate the inherent difficulty in finding roots with a good solution quality at reasonable computational effort with the current classical algorithms. Report the solution matrices obtained with the quantum state of and approaches on the quantum devices. And this is a MIRP with varying time horizon and qualitative comparisons, problem scaling. And here are the tables of the above topics. At last, we are going to discuss about numerical experiments, sequence-based formulation. For discrete sequence-based formulation, we consider both VQA with a standard hardware effort efficient analysis based on the single qubit rotations on 2 qubit entangling gates and the QAOA where parameterization of the circuit is constructed by alternate application of cost Hamilton by mixing the operator. And here is the sequence-based formulation with continuous time. Conclusion. Size, sparsity, connectivity, model faithfulness is difficulty to find optimal or may even feasible solutions are all characteristics of vehicle routing problem that depend heavily on specific instances of the interest and their mathematical formulation. Here we are provided the insights of characteristics of VRPTW. In particular, we have investigated those characteristics for 4 mathematical formulations enable to being solved on current quantum hardware. Good processing is also seems to influence a higher density of near optimal solutions of root-based formulation. However, the root-based formulation has unfavorable sparsity and connectivity characteristics, which are also important metrics to consider to near-term. Finally, for sequence-based formulation with continuous time, stimulations with a sequential convex programming solver than the shown practical convergence of ADMM heuristic to solutions with a large probability to feasible and optimal. The certain degree of inexactness is tolerated by ADMM algorithm and this promising feature to handle the inheriting noise affecting the quantum algorithms on real devices. Thank you.